This disclaimer was copied without permission.
Cheers, quaffers, guzzlers, swiggers, sippers and all other good people out there. Hopswatch here, and today I'm kind of stuck with all these industrial beers from the 6-pack test that I made in my last video. So I think I'll just have a couple of these and I'll look at this guy.
Hej, jeg hedder Ole. Ole Lokman, det er mig.
Hej Ole!
Jeg tror jorden er flad.
Oh. Just a sec. Well. You believe what? Okay. Ice and oven mitts won't be enough here. I'll need something different. Hold it. Oh, this'll work. I think. Now, what again?
Jeg tror ikke, at vi bor på en kugle, hvor vandet klistrer til den her bold, uden at falde af. Fordi, nå ja, det var på grund af tyngdekraften. Det havde jeg lige glemt. Der er nogle smarte nogen, der har fundet på tyngdekraft. Altså nogle matematikere, som har lavet nogle lange ligninger, hvor de beskriver tyngdekraften. Og det vil jo så sige, at nok falder de her ned, hvis jeg slipper dem. Men de tiltrækker ikke hinanden. Jeg kan i hvert fald ikke mærke nogen kraft, der får de her to lysestager til at komme tættere på hinanden.
Well, we have them in Denmark as well. Flat earthers. Ole Lokman here would be the most vocal one, with regular events around the country and appearances on TV news and whatnot. Now, you'll probably know most of the excuses that flat earthers come up with to try to legitimize their complete and utter dumbfuckery. If not, go watch Cool Hard Logic's video series testing flat earths and you'll be pretty much on top of it all. Cool Hard Logic is a fucking genius. Ooh, secret additional shout out there. Click the secretive link in the description to find out to whom. Now there are loads to take on in Ole Lokman's video. But let's just start with gravity. Now gravity. That is the force that makes my beer go into the glass instead of just floating out into the room here. It's industrial beer. It'll do for this. Ole, like so many flat earthers before him, doesn't believe gravity exists. And yes, you heard him correctly and saw him. He thinks that him not sensing any attraction between those diminutive candle holders disproves gravity. Now I have to grant him the fact that he knows that gravity is about masses attracting each other and not just a bigger mass attracting a smaller mass or some other nonsense like it being some kind of a universal downwards force actually gives him a more firm grasp on what the theory of gravity is about. And about him not being able to feel those candle holders' attraction to each other. You know, I've got a degree in sociology of religion and German language and history and culture, So I'm no natural scientist. However, still, the force with which those candle holders attract each other, I actually did the math on that. I usually get a bit scared when I see formulas with letters all over the place instead of just numbers. There's a reason why I chose an arts degree back in the day, but since I myself feel like I'm on shaky ground here, I'll walk you through the whole thing. The formula for calculating gravitational force of attraction, capital F, is actually quite simple. The attraction is measured in Newton, so once you plug in all the values, the figure you churn out will be in that unit. 1 Newton is the force that you will feel in your hand if you are holding an object with a mass of 1 kilogram. Say, for example, a liter of beer. The force that you can feel pulling downwards is the force that Earth's gravity exerts on the cans to accelerate them at a rate of 9.8 meters per second or meters per second squared towards Earth's center of gravity. Now for the next letters in the formula. The lowercase m's stand for the mass of the objects measured in kilograms. The small lower numbers simply denote that we are dealing with two objects and that m1 is the mass of object 1 and m2 is the mass of object 2. The lowercase r is the distance between the objects' centers of mass measured in meters. I saved the difficult one for last. The capital G is the universal gravitational constant. It may sound complicated, but it's actually just a number to plug in to find out how much force it takes to accelerate an object of a certain mass at a certain rate when the masses are at a certain distance from each other. It's a very small number, granted, but nonetheless, just a number. It's 6.67428 times 10 to the power of minus 11, or to put it in another way, it's this number. No, I'm not going to say all those zeros. Now for the other numbers in that equation. And please allow me to do a bit of guessing here, since I haven't been able to measure the exact mass or distance of the object that Ole is holding, as I have never met the man. But trust me, estimating instead of actually measuring will hardly have any crucial influence on the idea that you'll get from the result. Those are small, hollow candle holders, made of clay I think. Let's just be generous and say they weigh 200 grams each, that's 0.2 kilograms each. He's holding them rather close to each other, but remember here that you're measuring from the center of gravity, which would be in the middle of each. 10 to 15 centimeters is hardly far off. Let's say 12.5 centimeters, that's 0.125 meters. Now that we've got the values ready, let's get cracking. So the equation says masses multiplied with each other and with the universal gravitational constant over the distance between the masses squared. Simply fill in the numbers, crunch them, and the result you'll get is this number, which also would be called 1.70861568 times 10 to the power of minus 10. This is the roughly estimated force with which the two candle holders are accelerating each other towards each other by gravitational attraction. Now, just to give you an idea how excruciatingly insignificant that force is, remember that the force applied to your hand and arm when you are holding 1 kilogram of mass equals 1 Newton. The force pulling those candle holders together is approximately 5.8 billionth of the force felt when holding a liter of beer. It equals 0.17 micrograms. So take a new dollar bill. That would weigh 1 gram according to answers.com, and it would be about 15.67 centimeters long. Cut it in 1,000 equally small pieces along the wide side. They'd be 0.016 centimeters each, approximately. That's 0.16 millimeters, which is barely visible to the naked eye. But of course, they'd still have the full width of the original dollar bill, which is 6.6294 centimeters. Then cut one of those pieces into 1,000 equally small pieces, making each piece approximately 0.16 millimeters in one dimension and 0.07 millimeters, which is smaller than what the human eye can actually observe, on the other dimension. Now that's 1 microgram of dollar bill for you. But we're not finished yet. Remember that the force we got was equal to the weight of 0.17 micrograms, so we would need to slice those microscopic objects into further 6 pieces. And if you'd hold one of those pieces in your hand here on Earth, the gravitational pull from the Earth on it in your hand would approximate the attractional force between those candle holders that Ole is bouncing around in the video. The force is ridiculously small. Of course you can't feel any attraction at all between those objects. Any movement of air in the very room he's in will be immensely more powerful than the force that he's trying to gauge with his limbs alone. Now, if there's anyone out there watching who actually has a degree in mathematics or physics, I would really love you to go through my calculations to see where I've got them wrong. Because I kind of expect I did. However, it hardly matters how wrong I've got it, as the point remains that the gravitational force between the two objects is far, far too weak to be sensed in the most minuscule way by our crude ape appendages. So, I guess that'll be all for this time. I'll just sit here and drink while I'll be sobbing over the stupidity of mankind. You, however, contrary to me, should always remember to drink responsibly. And until next time, cheers. Like, just, well,